My name is John Ashley. I'm a solutions architect with NVIDIA. I focus exclusively on the financial services sector. I support our business development management teams, our ISV partners, and our hardware partners, both in North America and in Europe. I actually want to talk to you a little bit about a case study. And so what I want to talk about is just, can you do Longstaff-Schwartz Monte Carlo on the GPU, linked in from Mathematica? And so it may not be a problem that you would particularly attack this way, but it's a good example, it's interesting, and I think it highlights some of the benefits and the reasons you might do some of your calculations in CUDA. So what is Longstaff-Schwartz Monte Carlo? Everyone here probably already knows, but just in case someone doesn't do a lot of Monte Carlo, right, you're just doing Monte Carlo for American options. So the key difference, you generate the paths, you're evaluating the moneyness at the end, and then you come backwards through time and figure out, is this particular path in the money? And if it is in the money, is it better to exercise now, or do I expect that I would be better off waiting and exercising later? And then when you get done to at the end, you collapse all these paths and you form an expected value for whatever it is you happen to be pricing, whatever the option in question is. So the big contribution there on the from Longstaff and Schwartz is, how do you calculate that continuation value? And that is effectively just fitting a function for looking from the point in time you're at and the path values or the underlying values at that point in time, and looking out at the value of the paths that are in the money at all future times, fit a function to that, evaluate that function, and use that to estimate your continuation value. It's not hugely relevant to understand details of Longstaff-Schwartz or what kind of basis functions you pick for the rest of this. So that's sort of my review of Longstaff-Schwartz. And if I've gotten anything wrong, someone please be kind and correct me, because y'all are probably a lot smarter than I am at this point. So what is GPU computing, right? What is CUDA? What's GPU computing? Why is it special? What we really are isn't just GPU computing. What we really are is CPU plus GPU computing. We take full advantage of the fact that the CPU is a pretty incredible piece of hardware. It can do almost everything reasonably well. We use it to orchestrate, we use it to set up our jobs, we use it to control our jobs, we use it to tear our jobs down. We cooperate, with it, and we leverage its ability to manage the entire system. And so from that sense, even though we talk about GPU computing, we really mean CPU and GPU computing. And one of the things that Mathematica brings to the party, as a easy to manage scripting language and an environment for doing development, it makes it very easy for you to do the things on the CPU that it makes sense to do there, and only do the things on the GPU that you really need to do on the GPU to pick up the performance. The other feature of the GPU, if you think about what a GPU is for, it's designed to paint lots of pixels on screens really fast so that you could play cool video games. And it only needs to be able to do two things to do that. The first is it's got to push a lot of pixels out really fast, a lot of times a second. So it has very high memory bandwidth internal to the card. And every time it takes a light source and reflects it off a piece of steel and runs it through some fog so that you can see the smoke in front of whatever it is you just shot, every one of those calculations is floating point math, and most of them are transcendental functions. So it does lots and lots of floating point math really fast. That's about all it's good at. It can do other things, but those are the two things it's good at. So this is my "we're so much better than Intel" picture, and it looks this good because I've picked the only two things the GPU is good at. Obviously, if I picked some different things, these charts would look very different. Because as we've said, the Intel Core is all around a pretty awesome piece of machinery. So we're talking with our latest high-end compute cards, peak gigaflops double precision of over 500 gigaflops per card. And most of the major vendors will sell you a desktop that'll take 2 cards. So, okay, that's a peak of over a teraflop. The reality is, unless you're a crazy hand coder of tuned GPU code, you can expect to see between 200 and 300 gigaflops per card. Double precision. Closer to a teraflop single. So we really are good at math. If you can harness all that power, we can deliver on that. And in terms of memory bandwidth also, the internal bandwidth of the card is really high. And again, if your problem is, say, memory bandwidth bound or compute bound, like say the evaluation of Monte Carlo, of options with Monte Carlo, then you would think the GPU might be a good candidate if the CPU wasn't giving you the performance or the throughput that you were after. So the other thing that goes on is obviously just putting the GPU card in doesn't work. Your code does not magically get faster. Nothing works better with just our card in place. We work very closely with several vendors of mathematical packages. Mathematica is one of our premier partners. We work with a number of library vendors and a number of universities to do optimized parallel libraries. So for instance, you can call our optimized image processing libraries directly from within Mathematica if you wanted to do image manipulation. If you're doing numerical algebra, or if you need to do LAPACK kind of stuff or BLAS kind of stuff, there's libraries for that. Or FFTs, if you do a lot of convolutions in your math, the GPU is very good at FFT. And those functions are all, those libraries are all linkable directly from inside Mathematica. You could string all your stuff together normally, just as you normally would, and then just throw those bits out to the card if you're interested. You can get GPUs in all the major platforms, lots of research, all that good stuff. But the key thing here is it's about an ecosystem, and that's why we're excited to be here talking to you guys about how to integrate with Mathematica here. The underlying bit, if you're going to write custom kernels and invoke them from Mathematica, is you'll be writing them most likely in CUDA-C. OpenCL is an option. I'm not going to talk about it, but it is an option. Looks a lot like this. And all CUDA-C is C with a few extra keywords. So the bottom piece is how you would do basically some array math in CUDA, as opposed to the top piece, which is just how you would do it with a for loop. And in the bottom piece, you just, every thread is going to operate on one element of that vector. And it has some keywords that let it know where that thread is in the whole sea of threads you've launched, and now it knows what to do. So the code looks very much like C. These sort of global and this block IDX stuff is all very standard. It's a very repetitive template. Once you get your first CUDA code working, the rest of it's easy. There's a fair number of books, a lot of online tutorials, relatively straightforward. So we talked a little bit, right? Our cores aren't like their cores. Our latest cards are our compute card is a 448 cores, 6 gigabytes of RAM for those. The gaming cards go up to 512 cores at the moment, but those aren't exactly like Intel cores. Although they do have cache, they do have ECC memory, which if you're going into production is important to your IT guys. Probably all we want to say here. One of the interesting things is we group our cores in groups of 32, so when you do work, we actually work on it in multiples of 32 threads at a time. And each of those isn't quite an Intel core equivalent doing math, but we have a lot more of them. That's probably all we want to say here. Our threads aren't like their threads. We're going to talk about the fact that we launch a lot of threads to get stuff done to keep the card busy. Mathematica hides all the complexity of managing that for you, but our threads are very lightweight. We switch between them every clock cycle. It's not like writing multi-threaded code on the CPU, which again, Mathematica makes very easy for you to do because it hides a lot of that complexity. They also hide the complexity of launching thousands of threads onto the GPU. We do subdivide these threads into blocks, groups of threads that we're going to run together. What that lets us do is work within this memory model that has shared memory and global memory. And it gives us scalability. So whether we're running on hardware that has a couple of these streaming multiprocessors and sets of cores, or whether we're running on something that has lots and lots of cores, or with some number in the middle, the job will finish with the correct result every time. You're guaranteed, no matter how many cores are out there, that your threads will get consumed and executed correctly. So that was the Ultra Lightning tour. That normally takes 30 minutes, but didn't seem like that was the part that people were really going to be interested in. And no one has asked any questions yet, so I'm very disappointed. So how does this all work with Mathematica, and when you should be thinking about using GPU computing? So let's talk about how it works. CUDA Link is very straightforward. CUDA Link lets you ignore all the hard parts of CUDA C programming and of C programming in general. Suddenly you don't have to write data file manipulation stuff. You don't have to clean up memory. You don't have to worry about allocating memory. You can do all that in Mathematica, manage your data sets, manage your vectors and your arrays. All you do is you call your CUDA code. If you're writing a custom CUDA kernel, you grab that code, you stick it in as text, or you point Mathematica at the text file it's in, and Mathematica will take care of compiling it for you and integrating it with the flow of control and the other data that's in your Mathematica scripting. And then you just call it like any other function, as long as you're calling it with data that's out on the GPU. You get to control all the parallelism, and you can interact with it. So instead of having to, every time you want to test something new, you have to go back and go into your Visual Studio environment or whatever and recompile your whole C program and run it and test it. You get that interactive development that you get with Mathematica. So we talked about how, when, and why would you bother to write CUDA code, right? Why would you write C and integrate it with Mathematica? And part of it is that if you do that, you get supercomputer performance on your desktop. Realistically, where else are you getting 300 gigaflops on your desk? That's a relatively small machine. You can get machines with multiple cards. It is frequently the case that our customers that are doing GPU computing will on their desktop will outperform a small grid. I was working with an insurance company that was doing risk calculations with variable annuity life policies, which are commonly evaluated with Monte Carlo. They do stochastic on stochastic, so they run lots of Monte Carlo on that. And they have a large portfolio that this particular company operated across 7 countries. And the guy was running jobs that took their grid a week on his desktop overnight with CUDA processing, because forward Monte Carlo takes advantage of the fact that we have a lot of bandwidth and a lot of math capability. It also makes it very easy if you want to test out scalability. Let's say you are thinking of taking some new model into production, and it's a pretty complex model. It's very easy using the multi-threading capabilities in Mathematica to throw off 4 threads and then say, oh, by the way, each of you threads grab a GPU and do something with it. Suddenly, you have multi-threaded, multi-GPU code. That's a lot easier than doing that in C, where you have a process that you've got to do all the overhead of thread management. It's a lot easier even than doing it in Java. And then on top of that, Grid Mathematica is GPU aware, just like any other copy of Mathematica, which means if you want to suddenly go testing things on a cluster, or let's say you have some new risk analytics you want to try out. You want to look at taking your simple models and making them a little more complex. Because we all know as risk managers, we tend not to be able to run the full pricing model that maybe the front office guys are running, because we're valuing the entire firm's portfolio. Suddenly, you have the ability to try stuff out with an amount of compute that you would never get for a test run, and you can trim that development cycle down. So instead of having to kick off your new proposed risk model run on part of the portfolio, you can check it all. So all useful there. And the other side is, let's say you are thinking of going production with some C code. You can integrate that in And you get all the statistical and data visualization tools of Mathematica right at hand. Debugger, yep, I can go into the debugger. I can look at any particular point in memory I want, but I can't see it all in context. I can't graph the whole thing. I can't have the CPU version of the algorithm and the GPU version up, compare the values, and say, look and go, ah, yep, those are all right. I must have done my parallel port correctly. You can always hand that CUDA C code off to the C guys later. But you've now checked it, you're confident in it, you've seen the control flow. You could swap the GPU bits of the code in and out as you go. It's also a great place to test discrete math and precision issues. If you want to go back and forth and look at whether it would make sense to do certain parts in mixed or double or single, from a performance perspective, this gives you the turnaround time to check that at scale, as opposed to only being able to check it with toy problems. And why that's important is because on a small problem, you will never see summation issues with discrete math, right? So CPU math does a summation. You start at the beginning of the array and you go on. You're constantly adding an ever-increasing number, an ever larger number, to a number of some constant magnitude, and eventually you get precision issues. If you don't have a big enough set of data, though, you'll never see that problem. With the GPU, you can run big sets quickly. GPU math, actually, the normal way to do a summation there is in parallel. So you take the first half of the array and you add the second half to the first half, and you repeat till you have one entry left, which actually gives you a more precise answer. So you can actually compare whether you can discover whether you have a precision issue being introduced by your summations, if you have complex products, for instance. The new line of GPUs, the Fermi GPUs, are fully IEEE 754 compliant, so they are completely accurate. And you care about those precision issues because even your CPU is going to be twice as fast if you can do part of your algorithm in single precision. So even if you aren't planning on becoming a big GPU user, working with Mathematica on your desktop, you may be able to speed up your normal production grid code by a substantial amount by proving that there is no difference in your end result between single and double precision for some phases of your algorithm. On the professional GPU cards, we're also 2 times faster in single precision. Our gaming cards, if you're using your Mathematica and CUDA with a gaming card, those actually only have 1/4 of the double precision speed of the professional card. So it's actually 8 times faster to do single there. And finally, no matter whether you're on a CPU or a GPU, the bandwidth of your system just doubled. The bandwidth of your network doubled if you're moving singles around rather than doubles. So that can be an important thing to look at if you're trying to really optimize everything you can for speed or utilization. I could show a real quick example of the actual code. It's not that bad. This is the code to load some code out of a file, pass it the name of the routine, tell it what kind of input and output it's going to take. And then when you want to call this stuff, it's fairly easy. You just hear this CUDA memory load is explicitly moving this data from the CPU over to a structure on the GPU. And then all you do is call this function just like it's any other Mathematica function, and you pass it variables just like any other Mathematica function. And those variables, if they exist on the GPU, there's no more data movement at that point if they're already there. If they aren't, you've got to get them there. And then you can run through, for instance, this is the step that's actually making the asset paths for all the Monte Carlo that I'm going to do for this. And it also sets up the last cash flow step at the end. And then here I just do a loop on the CPU, walking backwards through time and invoking these routines, right? Find part 1, 2, and 3 are sort of determining the moneyness of the paths and setting up for some other calculation that's going on there. We're just call these routines just like they were anything else, just like a standard function. We make the regression matrix, we run our solver, we can set our cash flows, and away we go. So it's, you know, very much looks like.
Yep, there's a CUDA memory get
Yep, there's a CUDA memory get at the end, And this is one of the common, to your point, what we've done here is actually, in order to make it easy to check that the values are the same, we actually generate the random numbers on the CPU side and move them all over en masse, which we take a performance hit for doing. You would actually, in production, you would generate your random numbers on the GPU. So you wouldn't move, you'd move very little data for Monte Carlo other than the setup stuff, right? Initial strike, how many paths you want, etc. And then at the end, you really only want prices back. And so all you do is this CUDA memory get, and all the stuff in the middle, the only thing going across the wire is instructions from the CPU to the GPU to run this kernel that you already have. Right, I've already passed you all this code, run it with these parameters, run it with these parameters. And so you're sending very little tiny packets across that bus. And that's another thing that makes Monte Carlo very ideal for the GPU. Binomial, trinomial, PDEs, those also work. They're just not quite as ideal as Monte Carlo. Right, so this is one of the outputs of this. It's actually, this problem is computing an American put, so it's a simple thing. You could compute it many other ways. But it's computing a surface, a pricing surface for it. It's saying for a range of prices and a range of volatilities, for this option that's near its strike, what's the pricing surface look like? So it's actually calculating 400 points on the pricing surface, and it's calculating a full set of Greeks at each point. Well, full set. It's running 6 Monte Carlos to calculate 5 Greeks along with the price. And so brings us to one of the things about the GPU. If you look at this, if I run one case at a time, single Monte Carlo problem at a time on the GPU, I pay a lot of overhead because to calculate this 400-point surface, I have to make 400 round trips to the GPU, set the problem up 400 times, solve it 400 times. It takes 290 seconds on the GPU to solve that problem 400 times. I guarantee you the CPU will be faster than that. It's only taking it 0.7 seconds to solve each case. But again, I guarantee you the CPU is faster than that per case. But what happens if I've got plenty of room on the card. So if I set up 4 Monte Carlos on the card, so I solve 4 problems, plus I'm solving all the Greeks, so I'm really solving 26 problems at a time. My time to solve those 26 problems goes from 0.74 to 0.82. Almost no increase in time, but I've solved a lot more. I've solved 4 times more productive work. So my total GPU time drops to 82 seconds.
That time was really just the moving across the bus time, not the computation.
It's a combination of moving across the bus time and the fact that that one case is not saturating the computation on the card. I have 448 cores on the card. They switch contexts every clock cycle. To really fill up a GPU card, you really want 2,000, 3,000, 4,000 threads running at a time. And so one case, I can do that, but there's so many threads starting and stopping, it just doesn't work that. It doesn't saturate the card. 4 cases, I'm starting to get, the card's starting to get some traction. It's starting to get some work done before it's done. And so if you look at this graph at the top, this is a log scale. So this green line is the number of paths we're evaluating. So at the far end, I'm solving 25 cases at a time. And again, it's very easy to batch this work up with Mathematica as a scripting language and check that you've done the batching right and everything else. You can graph that surface. You could compare it. You can run through all these cases. You could use manipulate to set all these parameters and change the option prices and the whole surface and calculate, instead of just a chart or a single number, you can calculate whole surfaces very quickly this way. But as I go up, when I solve 25 at a time, I'm doing 25 times as much work in roughly twice the time on the GPU. So instead of running 400 iterations to compute my surface, I'm only doing 16 iterations to compute my surface. So my total time is only 25 seconds on the GPU. So one of the great things about the GPU is if you can get one thing working on it and you have room on the card to solve a lot of that thing, the rest of it's effectively free.